Welcome once again to Dave Does Math from Home. This is the thrilling conclusion to our trilogy of section 3.1. This is sort of our introduction to derivatives. Derivative means that we've taken the idea of slope, and instead of looking at 2 points, we looked at 1 point and the distance, a distance away from that. So you have 1 point and some distance away from that, and then we took the limit as that distance shrunk to 0. So that instead of having a secant line between 2 points, we have a tangent line at 1 point. And we're looking at the slope of that tangent line using limits of difference quotients. That's the idea of a derivative. There's one more kind of function I want to show you how to do the derivative for. It's an exciting one. I want to know what happens if we look at f of x equals the square root of x plus 5. I want the derivative, or the slope of the tangent line when a is 4. And as always, step 0 is we write down what m tan means. M tan means we're taking the limit as h goes to 0 of the difference quotient f of a plus h minus f of a all over h. And we know what a is, and we know what f is, and we know what h is doing, so all of this is very solvable. Step 1, we rewrite this limit, but now we're going to plug in f and h into this business. So f means that we're going to do the square root of something plus 5. And that something is 4 plus h plus 5 minus f of a should give us the square root of 4 plus 5. And all of this is over h. So I plugged in a plus h to the function here, and I plugged in a, which is 4, to the function here, and now I have this. And I probably could simplify this. I could turn this into a, I probably should actually. Let's simplify what's going on under the square roots of it. This is the square root of 9 plus h minus the square root of 9 all over h. And we still can't plug in h equals 0 because it's still in the denominator. We have not yet simplified this enough to successfully execute plan B. So we need to simplify it some more. And we're going to simplify this some more using conjugates. The only way I'm going to deal with this h on the bottom, h in the square root nonsense is if I multiply this thing by the conjugate. Root 9 plus h stays there. Root 9 stays on the back end. Conjugate means I'm going to change the sign. And I'm going to multiply that by on the top and on the bottom. So I'm not actually changing anything. Let's see what happens when we do this. When you multiply this on the top, you should end up with a difference of squares. This is a minus b times a plus b. So you should just get, and if you don't believe me that you should get this, you can FOIL this out if you want to. But because this is a difference of squares, we very deliberately made it be a difference of squares by using conjugates. Because it's a difference of squares, we should get a squared, which is 9 plus h, minus b squared, which is just 9. So 9 plus h minus 9 is what we get on the top. On the bottom we get h. I'm not going to distribute this. I'm just going to say h times the square root of 9 plus h minus the square root of 9. And I know I could figure out what the square root of 9 is. I'm just sort of not interested in it. I'll deal with that later. For now, I want to simplify the top. Positive 9, negative 9, that cancels. The only thing left on top is an h. H over h. That cancels, just leaves me with a 1 on top. So this is now the limit. H goes to 0 of 1 over square root of 9 plus h. I'm sorry, this is plus. Plus on the bottom. Plus the square root of 9. This is the step where the h's have canceled. Now I can successfully execute plan B. When I plug in 0 for h, I get 1 over root 9 plus root 9, which is 1 over 6. Now I will admit that the square root of 9 is 3. I get the 3 and the 3, and that's just 6. This is the slope of this function when a equals 4, which makes sense. Square root x plus 5 is a square root function that has been shifted 5 units to the left. So 1, 2, 3, 4, 5. This is where my square root function starts, back here at negative 5. And it does this. So out here at 4, I should have a very, very, very flat tangent line. The function is continuing to sort of curve. This is the tangent line. And the slope is small, 1/6. So positive, but almost flat. That's it. Those are the 3 big kinds of functions that we're going to be doing limits of difference quotients for. Eventually we're going to take derivatives of lots and lots and lots of other cool functions. It's going to turn into a mess. There's a lot that we need to do. But by the time we get to the other functions like exponentials and trig functions and logarithms, by the time we start taking derivatives of those, we will have some shortcuts and we won't have to use these limits anymore. Because this is, I think we can all agree that this is a super fun process. Definitely agree with that. It's important to me. We can agree that this is super fun, but it's also pretty time consuming. So if we can find a way to get these derivatives, these tangent slopes, without taking the limit of a difference quotient every time, we should. But for now, we don't have these shortcuts. We're gonna do it the hard way for the easy problems. We'll get the shortcuts later. It'll be nice. If you have any questions, email me. Other than that, I'll see you in section 3.2.